Right now, somewhere in a massive climate-controlled warehouse, a mechanical arm is twitching with microscopic precision, or a specialized laser is firing a pulse of light into a layer of synthetic dye, all just so you can save a single photo of your lunch or a document for work. We live in an era where data is the new gold, but we rarely stop to think about the vaults we keep it in. We take for granted that when we hit save, our information stays there, waiting for us, even when the power goes out. But the history of how we've managed to trap information into physical objects is a saga of pure engineering madness, desperate innovation, and some of the most fragile physics ever utilized by mankind. Today, we are deconstructing every major evolution in secondary storage, from the days of literal holes in paper to the modern era of high-speed silicon and the experimental future of glass and DNA. We are exploring how we turned the abstract concept of a thought into a permanent physical record. If you've ever wondered why your old hard drive makes that clicking sound, or how a tiny USB stick can hold more information than a room full of books, you are in the right place. Let's dive into the silicon abyss of storage technology. To understand where we are, we have to travel back to a time when data was something you could actually touch and tear. This was the era of punch cards. Imagine a piece of stiff paper with rows and columns of potential positions. If you wanted to tell a computer a number, you punched a hole in a specific spot. No hole meant 0. A hole meant 1. This was binary in its most primitive, physical form. Thousands of these cards would be fed into a machine that used metal brushes to sense where the holes were. If the brush made contact with a metal plate through the hole, a circuit was completed. These weren't just for early computers, they were used for weaving looms and player pianos long before the electronic age. But for computing, they were a nightmare. If you dropped your box of cards and they got out of order, your program was essentially gone. They were slow, they were bulky, and they were incredibly susceptible to humidity. But for decades, this was the gold standard of data storage. It was the moment we realized that information could be recorded as a physical state that a machine could read back later. By the 1950s, the industry needed something faster and more dense. This led to the adoption of magnetic tape. If you've ever seen an old spy movie with giant reels of tape spinning back and forth, you've seen this technology in action. It works on the principle of electromagnetism. The tape is covered in a thin layer of iron oxide, basically rust. When the tape passes under a recording head, a tiny electromagnet flips the polarity of the magnetic particles on the tape. North is a 1, south is a 0. This was a massive leap forward because you could overwrite the data, something you couldn't do with a punch card. However, tape had a giant flaw. It was sequential access. If you wanted to read a file at the end of the tape, you had to wait minutes for the reels to spin all the way there. It's like having a book where you have to read every single page in order just to get to the last chapter. While we don't use tape for our home computers anymore, it is still quietly running the world's biggest data centers. It is incredibly cheap and can last for 30 years without losing its data, making it the ultimate cold storage for government records and scientific data. But the real revolution happened in 1956 with the invention of the hard disk drive, or the HDD. The first one, the IBM RAMac, was the size of 2 large refrigerators and held about 5 megabytes of data. Barely enough for one high-quality song today. It introduced the concept of random access. Instead of a long ribbon, the data was stored on spinning circular platters covered in magnetic material. A mechanical arm with a read-write head would zip across the surface, meaning it could jump to any piece of data almost instantly. This changed the way we interact with computers. It meant we could have real-time operating systems and databases. Over the next 60 years, the HDD became a miracle of miniaturization. Scientists figured out how to make the magnetic grains smaller and smaller, and they developed GMR, or giant magnetoresistive heads that could sense even the tiniest magnetic fields. Today, your standard hard drive has a head that flies above a platter spinning at 7,000 revolutions per minute. At a height that is less than the thickness of a human hair, it is the equivalent of flying a jet plane at Mach speed, 1 inch off the ground, and counting every individual blade of grass without ever crashing. When your hard drive clicks, it's often that mechanical arm failing to find its place. An audible reminder of how fragile this mechanical ballet truly is. As computers entered the home in the late 70s and 80s, we needed a way to move data from one machine to another. This gave birth to the floppy disk. Younger viewers might only know this as the save icon, but it was a real, physical object. The first ones were 8 inches wide and actually floppy, consisting of a magnetic disc inside a thin plastic sleeve. Then came the 5¼ inch version, and finally the iconic 3½ inch disc with the hard plastic shell and the sliding metal shutter. They didn't hold much, usually 1.44 megabytes, but they were the social network of their time. You'd trade games, documents, and pictures by physically handing someone a disk. The floppy era taught us about data corruption. A single magnet, a bit of dust, or even a hot day could erase your school project. It was our first experience with portable personal storage, and it paved the way for the high-speed connectivity we have today. By the 90s, the world was moving toward multimedia, video, and high-quality audio. Magnetic storage was struggling to keep up with the demand for cheap, high-capacity distribution. This led to the era of optical storage, the CD-ROM, the DVD, and eventually the Blu-ray. Instead of magnetism, these used light. A laser would shine onto the surface of the disc, which was covered in billions of microscopic pits and lands. If the light hit a flat spot, it reflected back to a sensor, a 1. If it hit a pit, the light scattered a 0. This allowed for massive amounts of data to be pressed onto a cheap piece of plastic. The transition from CD to DVD and then to Blu-ray was essentially a race to make the laser's wavelength shorter. A red laser is relatively wide, so the pits have to be big. A blue laser is much narrower, allowing you to cram 5 times more data onto the same size disk. Optical media was the king of the world for 20 years, but it had one major weakness. It was slow to write to, and the disks were notoriously easy to scratch. As internet speeds increased, the physical disk became an endangered species. But while we were spinning disks and tapes, a new technology was quietly evolving in the background. Flash memory. This is the solid-state era. Unlike everything we've talked about so far, flash memory has no moving parts. It doesn't use magnetism or lasers. It uses trapped electrons. Inside a flash chip, there are billions of floating gate transistors. By applying a specific voltage, you can tunnel electrons into a tiny island of polysilicon where they stay trapped even when the power is turned off. If the island is full of electrons, the transistor's threshold voltage changes, which the computer reads as a 0. If it's empty, it's a 1. This is the technology inside your USB thumb drives, your SD cards, and your smartphone. It is incredibly fast, it is silent, and it is resistant to physical shocks. You can drop a USB drive off a building, and your data will likely survive. Do that to a spinning hard drive, and it's game over. This leads us to the current king of storage, the solid-state drive, or SSD. In the early days, SSDs were prohibitively expensive and had small capacities. But as we learned how to stack these layers of transistors on top of each other, a technology called 3D NAND, capacities exploded and prices plummeted. Modern SSDs use the NVMe protocol, which allows the storage to communicate directly with the processor at blistering speeds. We've moved from hard drives that move 100 megabytes per second to SSDs that can move 10,000 megabytes per second. This is why modern computers turn on in 5 seconds instead of 2 minutes. However, flash memory has a unique quirk. It wears out. Every time you trap those electrons, you cause a tiny bit of physical damage to the silicon. After enough write cycles, the cell can no longer hold a charge. Modern controllers use wear leveling to spread the data around and ensure the drive lasts for a decade or more. But it's a reminder that even silicon has a lifespan. We also have to discuss specialized storage like the micro SD card. It is a miracle of manufacturing that we can fit 1 terabyte of data, the equivalent of a small library, into a piece of plastic smaller than a fingernail. Inside that tiny shell are several layers of silicon chips stacked like a skyscraper and connected with gold wires thinner than a spider's silk. These devices are the backbone of the mobile revolution, allowing cameras and phones to record high-definition video in real time. But because they are so small, they are extremely sensitive to heat and electrical interference. Not all micro SD cards are created equal. Some are built for speed, while others are built for endurance, like the ones used in dash cams that have to record constantly for years. In the enterprise world, there is a concept called RAID, redundant array of independent disks. This isn't a single device, but a way of using multiple drives together. You can stripe data across 2 drives to make them twice as fast, or you can mirror the data so that if one drive fails, the other has a perfect copy. This is how data centers ensure that your emails and your bank balance don't just vanish because a single hard drive decided to quit. It's the philosophy of safety in numbers applied to digital information. RAID is the reason why the cloud feels so permanent, even though it's actually made of thousands of individual, fragile components. Let's look at a storage type that most people forget about. The SIM card. Yes, that little chip in your phone is a storage device. It holds your unique identification keys, your contacts traditionally, and small bits of network data. It is a secure element designed to be incredibly hard to hack or copy. It's a very specialized, very slow, but incredibly robust form of flash memory that acts as your digital passport to the cellular network. In the near future, these are being replaced by eSIMs, where the storage is built directly into the phone's motherboard, making the physical card a relic of the past. We should also talk about the controller. Every storage device, from the cheapest USB stick to the most expensive enterprise SSD, has a tiny computer inside it called a controller. This chip is the brain of the device. It manages where the data goes, it fixes errors using math called error correction code, and it handles the communication with your computer. If the controller fails, your data is often gone, even if the storage chips themselves are perfectly fine. This is why data recovery is so difficult. It's not just about reading the raw bits, it's about understanding the secret map that the controller used to organize those bits. What about the external storage? We've gone from clunky external hard drives that required their own power brick to tiny, portable SSDs that can fit on a keychain. The evolution here has been driven by the bus, the connection type. We went from slow USB 1.1 to USB 4 and Thunderbolt. A modern external drive can now be just as fast as an internal one, which has changed the way creators work. You can now edit 4K video directly off a drive that is plugged into your laptop's side port. This portability has made our digital lives liquid, allowing us to carry our entire workstation in a pocket. But we are reaching the limits of silicon. As we try to cram more and more data into flash memory, the walls between the electrons are getting so thin that they can't hold the charge reliably anymore. This is why researchers are looking into the 5th generation of storage. One of the most promising is glass storage. Using a high-speed laser, we can create microscopic voxels, 3D pixels, inside a block of quartz glass. This is 5D storage, because the data is encoded in the size, orientation, and position of these voxels. Glass storage is virtually indestructible. You can bake it, flood it, or subject it to electromagnetic pulses, and the data remains. It could last for billions of years, making it the ultimate time capsule for humanity. Then there is the most organic storage imaginable, DNA storage. Nature has been storing the blueprints for life for billions of years using A, C, T, and G. Scientists have figured out how to convert binary code, ones and zeros, into these 4 chemical bases. We can now print data into synthetic DNA and store it in a cool, dry place. The density is staggering. You could fit all the information ever created by humanity into a single room if it were stored in DNA. However, the current problem is speed. Writing and reading DNA takes days, not milliseconds. It's not for your gaming PC. It's for the long-term survival of human knowledge. It is the ultimate bridge between biology and technology. Let's not forget holographic storage. This has been the next big thing for 30 years but has struggled to find a market. It involves using 2 lasers to create an interference pattern inside a light-sensitive crystal. Instead of writing data on the surface, it writes through the entire volume of the material. A single crystal the size of a sugar cube could theoretically hold a terabyte of data. While it hasn't become a household name yet, it remains a fascinating look at how we can use the fundamental properties of light to beat the density limits of magnetism and silicon. We also have to consider the cloud as a storage device. While we call it the cloud, it's really just someone else's computer. But for the average user, the cloud has changed the concept of storage from a physical object to a service. We no longer worry about how much space is on our phone. We just buy another 10 gigabytes of space in the air. This shift has massive implications for privacy and ownership. When your data is on your own hard drive, you own it. When it's in the cloud, you are essentially renting access to your own memories. The storage device has become invisible, integrated into the fabric of the internet itself. Across all these generations, the most important metric has always been density. In the first generation, we could store 1 bit in a vacuum tube the size of a light bulb. In the second, we could store it in a magnetic grain visible under a microscope. By the fourth, we are storing it in a space smaller than a virus. This relentless march toward the microscopic is what has allowed our digital culture to explode. Without this progress, we wouldn't have high-definition video, complex AI models, or even simple social media. Every piece of code we write and every photo we take is a load that our storage devices have to carry. But what about the digital dark age? This is the fear that because our storage media is becoming more and more complex, it might actually be more fragile. A punch card can be read with a magnifying glass. A magnetic tape needs a complex machine. An SSD needs a sophisticated controller and a specific software driver. If our civilization were to stall, would a future archaeologist be able to read our SSDs? Probably not. This is why endurance is becoming as important as density. We are building faster and faster vaults, but we are also realizing that they might not last as long as a stone tablet or a piece of parchment. Think about the interface of these devices. We've moved from physical cards to SATA cables, to M.2 slots, to the invisible air of Wi-Fi and 5G. The way we talk to our storage is becoming more abstract. In the past, you had to tell the computer exactly which sector of the disk to look at. Now you just ask for a file by name, and a dozen layers of hardware and software work together to find those trapped electrons or those magnetic patterns. The complexity is hidden behind a simple File Explorer window, but underneath is a chaotic world of error correction, wear leveling, and bus arbitration. Another specialized type is warm storage. Write once, read many. You see this in specialized SD cards or optical discs that cannot be erased. These are used for legal and medical records where the integrity of the data is paramount. You can't hack a worm disk to change the past. Once the physical change is made to the material, it is permanent. It is the digital equivalent of ink on paper, providing a truth that can't be altered by software. There is also cache memory. This is the sprint storage that lives on your processor or inside your hard drive. It's a very small, very expensive, and very fast type of memory that holds the data you are using right now. It is the most volatile and transient of all storage, but it is the secret to why computers feel snappy. It's like a chef having the salt and pepper right in front of them instead of having to walk to the pantry every time. As we look at the evolution of everything from the 11-inch platters of the RAMac to the microscopic transistors of a modern NVMe drive, we see a pattern. We are moving away from the mechanical and toward the electrical and photonic. The fewer moving parts we have, the faster and more reliable we become. We are trying to make our storage act less like a physical drawer and more like a part of our own memory. We want it to be instantaneous and eternal. So, the next time you hear your computer fan kick on or you see that little light blinking on your USB drive, remember the journey we've taken. Remember the room-sized machines and the boxes of punch cards. We have conquered the physical limits of our world to create a space where we can store the sum total of human thought. It is the most impressive hoarding project in history. But it's also a responsibility. Our data is our legacy, and the devices we choose to store it in will determine how much of that legacy survives for the next generation. Your role in this digital ecosystem is to be the curator. Don't just trust that the cloud will always be there. Have backups. Use different types of storage. Understand that every device has a lifespan and a purpose. Use an HDD for your massive collection of movies, an SSD for your operating system, and a piece of optical media for your most precious family photos. The silicon abyss is deep, but it's also organized. By understanding the tools we use to keep our digital lives alive, we can ensure that our information remains ours, safe from the bit rot and the mechanical failures of time. Every generation of storage has had its critics. People who thought we'd never need more than a few megabytes, or that flash memory would never be reliable enough for a primary drive. But history has shown that we will always find a way to fill the space we are given. We are a species of storytellers, and we've built increasingly complex jars to hold those stories in. From the first hole in a piece of paper to the first voxel in a piece of glass, we are proving that even the most abstract idea can find a permanent home in the physical world. Stay curious about the hardware. Stay vigilant about your backups, and never stop questioning how and where your data is being kept. We are living in a historic era, where the very nature of memory is being redefined by silicon and light. You are part of the most information-dense generation in history, equipped with vaults that would have seemed like magic to the people of the 1950s. Use that power to preserve what matters. The silicon abyss is open, and the next breakthrough is just a discovery away. Thank you for taking this deep dive into the physical reality of our digital world. Your information is your power, so respect the hardware that holds it, and it will continue to serve as the silent guardian of your digital self. Stay smart, stay backed up, and keep looking toward the future of the infinite archive.